Hi, my name is Sinjin Sharma. I'm doing this project with my partner David Tran, who you'll hear from in a little bit. We're doing this for our CFD 4301 class, and this is a CFD analysis of a pontoon boat. So first, an introduction. Fluid dynamics is a sub-study of fluid mechanics and has to do with the flow of fluids, which are liquids and gases. Computational fluid dynamics, or CFD, is the analysis of systems involving fluid flow, heat transfer, and associated phenomena such as chemical reactions through computer-based simulation. The program we're using is ANSYS Fluent Workbench. So just some quick fundamentals. Generally, when you're making a 3D model, you're going to have an inlet, an outlet, and a control volume. There are 4 variables associated with this: a U variable, a V variable, which is velocity, a W variable, and a P variable, which is pressure. These can be described in the very complex Navier-Stokes equations, but essentially what the program does is it takes our inputs, calculates these Navier-Stokes equations, and gives us a 3D model output. So there are many different applications for CFD analysis. One is aerodynamics, say the forces that act on a car moving through air. Another is hydrodynamics, the forces that act on a boat or submarine moving through the water. This can be applied to electronics, so the air moving through a cooling system, say in a computer. Biomedical engineering, you can see how air moves through the lungs or blood moves through the heart. Meteorology, how different storm systems are predicted to move. And this can also be used in chemical process engineering or environmental engineering. So CFD models the actions of fluids in a system. It provides a visual model of forces that are not easily seen in physical tests. So you can't really see air pushing against a car, or you can't really see the high pressure areas of water pushing against a boat. So it allows for an initial analysis of designs before more costly prototypes or physical tests are conducted. So for our problem, we performed a 2D analysis of a pontoon boat with 3 pontoons traveling through the water at 2.5 meters per second with an angle of attack of 5 degrees. We simulated a top-down view and assumed that the water flow was transient. So here's the geometry that we made. This is about a 1:5 scale to an actual pontoon boat. Each one of these pontoons is exactly 1 meter long. They are each 0.1 meters across, and they are each 0.1 meters apart. And the reason we scaled this down is because of processing power. If we made it the actual size of a pontoon boat, it would have taken way too long to generate. Our testing area is made of an arc, or a half circle, and a rectangle. The radius of the half circle is 6 meters, and the length of our rectangular area is 7 meters.
The first step is to open Workbench and select Fluid Flow Fluent. Next, we change the geometry setting to 2D. Once we open the Geometry Designer, we enable the grid, enable Snap, and change the major grid spacing to 0.05 meters. This is done to make the creation of our pontoons easier and may be done differently based upon personal preference. Now we create our pontoons by drawing 2 diagonal lines 0.1 meters long and 0.1 meters high, and a rectangle that's 0.9 meters by 0.1 meters, and trim out the left-hand side of the rectangle. Once we have the dimensions correct, we replicate the pontoon 2 more times, each 0.1 meters away from the one next to it. Once we are done, we generate the pontoons. Next, we create a second sketch to draw the test area. We first draw an arc with a radius of 6 meters and an attached rectangle with a length of 7 meters, and trim out the left-hand side of the rectangle. Once we have finished the drawing, we generate the area drawing and change the operation to add frozen. Next, we create a boolean and change its operation to subtract. The area generation is selected as the target body, and one of the pontoons is selected as the tool body. Once this is generated, the area of the pontoon will be subtracted from the test area. We repeat this process for each of the pontoons.
After the geometry is done, we then can proceed to do the meshing. Here we are naming the different entities. First doing the arc circle as the inlet, the back face of the rectangle as the outlet, and the pontoons as pontoon walls. The other two sides of the wall don't need to be labeled as ANSYS will acknowledge them as walls in this case. This is to ensure that the different entities are labeled. Next, we will do a method of triangles with a refinement of 3. Then, we will do an edge sizing on the pontoons of 0.02 meters with a hard behavior. Here in the middle, we can see how small and close the meshing is. This is to ensure that the results shown will be accurate. Then we will go under the mesh details by clicking the mesh on the left and change the element size to 0.5 meters. There are many ways to go about meshing, and we found this to be the easiest method that will still give accurate results that will be needed for us.
Now we begin our setup. In the Fluent Launcher, we select Double Precision, change the processing options to parallel, and change the number of processes to 4. This allocates what part of the computer will perform the model generation. Once the new window opens, we change the time setting under General to Transient. Under Models, we select Viscous Laminar and select K Epsilon. After that, we change the K Epsilon model to Realizable. Next, we go into Materials and Fluids and change the fluid from air to liquid water. Next, under Boundary Conditions, we change the velocity specification method of the inlet to Components. Next, we specify the x and y velocities. We find these by multiplying our velocity of 2.5 meters per second by the sine for y and cosine for x of our 5-degree angle. We then change the specification method to intensity and length scale. We then make the same specification change for the outlet. Next, we go to Residual Monitors and change the continuity, x and y velocities to 1e to the negative 6. Next, we go to Solution Initialization. set it to standard initialization, compute from inlet, and initialize. After this, we go to solution animations and set it up for velocity and pressure contours. This is what allows us to see the videos in the end. The last step is to go to Run Calculation, change the time step to 0.1, change the number of time steps to 250, and set the max iterations to 30. This will determine how long the simulation will run. Finally, we run the calculation.
So here we have our velocity contour. Here we can see that the water directly contacts the front of our partisans at about 2 meters per second. Water that is pushed between and around the pontoons increases in velocity to about 2.5 meters per second. Water directly behind the pontoon has a very slow velocity of less than 1 meters per second. Overall, this is the result that was expected for our velocity contour. Next, we can see our pressure contour. As the video shows, there is a high pressure area where the water contacts the front of the pontoons and low pressure pockets on the outside of the pontoons. These low pressure areas exist because the water is contacting the pontoons at a slight angle and not directly along the x-axis. The pressure around the pontoons is constant because there is nothing for the water to push against. Overall, this is the expected result from the pressure contour.